So I try to record. And so welcome to our condensed matter general club. So we will continue our weekly meeting this semester, for this semester. So today, since no one signed up, so I just volunteered to talk about my recent work with Zhuven on deconfined quantum criticalities among grand unified theories. So here are some references. We have several recent works so about this topic, but today's talk is more concentrated on the first part, on the first work that we have done. Okay, so for the students, if you have any ideas or anything you want to talk, please also sign up our journal club series. Okay, so so let me start. So let me first thank my collaborator, Zhuven Wang, and most of these works is driven by Zhuven, and he basically is supervising me doing many things. So I also learned a lot. So the things that we are looking into is a grand unified theories. So as condensed matter physicists or theorists, we may have a different view of our universe. So one open questions in high energy physics is how strong, weak electromagnetic forces in standard models are unified at high energy. That is basically the goal of people studying grand unified theory, try to unify all the known gauge forces in our standard model. So the conventional or maybe most typical perspective of how do we view the grand unified theories is this perspective number one is that smaller gauge groups gradually merge into larger gauge groups at higher energy scales, because in this standard model framework, each kind of interaction is described by a gauge theory, and where the forces, for example, strong, weak, or electromagnetic forces are all mediated by these gauge fields, and gauge field is specified by gauge groups. To unify the gauge forces is try to find a larger gauge group that contains all the smaller gauge groups. Then the force will be mediated by a unified larger gauge force. So that's the idea, and another assumption is that this happens at higher and higher energy scales. Maybe at the higher energy scales, all gauge the difference between different kinds of forces may vanish, and eventually there is a unique all-encompassing gauge theory that unifies all gauge forces. So that kind of picture is more like the standard model is describes the fundamental particles that we know in our universe nowadays, but maybe in earlier universe, when the energy scale is higher, there can be other larger gauge groups that unifies our standard model gauge forces. But in this work, we try to look from another perspective, which is this perspective 2, which is closer to maybe more familiar to condensed matter physics ideas, is that we look at all these different gauge theories as different effective theories of different quantum phases. And we consider the standard model is only one possible phase among many adjacent phases of our universe. So our universe is a big quantum many-body system. Of course, it can have many different phases. And if it is in different phases, then there are different low energy effective theories, which may correspond to different grand unified theories or different gauge theories, maybe not unifying our force, but at least similar to standard model, or maybe in its adjacent phases. So in this picture, there is not an ultimate theory, not an all-encompassing unifying theory. We are not trying to seeking for the ultimate truth, but otherwise we are trying to explore the much richer landscape of all the possible phases in the universe, and more importantly, the phase transitions among these phases. So both the standard model and various grand unified theories that existed in literature are generally described by the Yang theory, which is a theoretical framework, which you have some non-abelian or abelian, doesn't matter maybe, but in general, non-abelian gauge field, which couple to fermionic matters. And the fermionic matters, the difference of all different kind of theories lies in the choice of matter contents and also the gauge groups. So for standard model, each generation of the matter particles contains 16 or 15 Weyl fermions. So because there's a question mark for 15 because the 16th Weyl fermion in each generation is correspond to the stereo neutrino, which is the neutrino that does not participate in strong, weak, and electromagnetic forces interactions. So that has not been justified or falsified by experiments yet. But there's belief that maybe it exists or maybe it does not. So let's not try to comment that here. But in this work, basically, we will take the assumption that there are 16 Weyl fermions in each generation. And we will focus on one generation of the fermions. So that's the choice of the fermion content. So there are 16 Weyl fields here. And then they live in a 4-dimensional space-time, which is the space-time of our current universe. And then it couples to some gauge field. And the gauge bosons basically mediate the gauge forces between these fundamental fermions. So these fermions basically correspond to quark and leptons in our universe. And then different gauge theories are related to each other by Higgs transitions, because different gauge theories, basically the key difference is the gauge group is different. And then in order to go from one larger gauge group to some smaller gauge group, you need to break the gauge group or the gauge symmetry. And then this is fulfilled by basically condensing some Higgs field. So, so the transition that is going from one gauge group to another gauge group is generally Higgs transitions where the Higgs field will condense. And these Higgs field, the particular form of the Higgs field will be introduced later in addition. It is not, I didn't write any Higgs field in this very simple Yang theory yet, but we will introduce them later. Okay, so that's the general framework. So maybe let me take a little bit time to basically go through or review some of the fundamentals of particle physics, and then and it's also an opportunity that I can introduce some of the grand unified theories that is considered in our work. So let's start from the our current, like a common knowledge of a standard model. So standard model is a very successful model that describes very many phenomena of fundamental particles in nowadays universe. So it contains each generation 16 fermions, which includes quarks and leptons. So here are the quarks and these are the leptons. So the quarks you have up, for example, in the first generation, they are up, down, and each up quark has 3 colors, down quark also has 3 colors combined with electron and electron neutrino, that's the leptons, and then combine with their right-handed antiparticles. So altogether there are 16. And then we can label or arrange them by the charge that they carry under different gauge groups. So basically the gauge group describing the standard model is SU3 color times SU2 weak, times U1 hypercharge times U1 X. So this U1, so SU3 is the familiar describe the strong interaction between the 3 colors of the quark, and SU2 left correspond to the isospin, weak isospin symmetry, and then this U1Y is the weak hypercharge, and they together basically unify into this electroweak interaction. And then U1X is an additional symmetry of the standard model. You may consider to gauge it, but currently we can treat it, we can basically we can treat it as a global symmetry if we do not gauge it. So it is related to the baryon minus lepton number. So there's a baryon minus lepton number conservation in the standard model, which is captured by this U1 X symmetry. So let's say the internal gauge or symmetry group of the standard model is basically this group. And then the notation, this times with a subscript Z6 means that the two group is sharing some Z6 common group elements. So those Z6 subgroup need to be quotient. So, okay. And then there are different ideas.
So maybe I just add some comment if we can. So first is that the 16 biofermion model is one type of model we study particularly in this quantum criticality model. But I think you also mentioned, I just want to point out that it could be that our vacuum may not contain the 16 biofermion, the question mark there. But it's also very good to study this toy model as a possible vacuum next to the standard model vacuum. So by just for the reason to explore physics near the standard model vacuum, I think still worthwhile to explore, even though we may not really know where they are there. And another comment is that Yi-Zhuang You particularly studied the Mars Z6 gauge group, because later on we would like to embed to a larger Grand Unified gauge group like spin 10, and that's why we model the Z6. But it could also be that this Mars Z6 charge can change to Mars ZQ, where Q can be some 1, 2, 3, 6. But in our work, in particular here, we do the Z6.
Right. So yeah, that's right. Thank you for Juven's comment. So there, I think the punchline is that there are many different possibilities to explore. So I'm, although we are the work that I'm presenting here is one minimum possibility that we explored in our paper. So there are ideas to unify all these particles or the forces between these particles. So one famous model is the Pati-Salam model. The idea is is to try to unify quark and leptons by treating lepton as the fourth color. So if you look at the quarks, they have 3 colors. And if you treat lepton, which I already draw as a purple color, as the fourth color of the quark, then basically the gauge, the color group is enlarged from SU3 to SU4, which rotates all these quark and lepton together to each other. So this is one way to unify quarks and leptons. And also one can introduce another SU2, which rotates the right-handed fermions as well. So in this case, the gauge group is enlarged basically to SU4 cross SU2 left, which is the which is the flavor rotation between the left-handed fermions, and SU2 right for the right-handed fermions. But after this particle hold, after this charge conjugation transmission, they are all transformed to the left-handed Weyl fermions in our theory. So so these groups basically is also it can be equivalently written as a spin 6 cross spin 4 quotient Z2. So that is the gauge group of the Pati-Salam model, and this fermion transforms as a 4-to-1 representation under this either I can, so here I'm using Lie algebra instead of Lie group, trying to avoid these subtleties of quotienting some shared common groups. But the idea is that the representation is basically all these fermions are unified into this representation, and so there are only 2 separate representation of all the 16 fermions. So there's another scheme which unifies the quarks and leptons and or unifies the strong and weak forces, is by thinking that, okay, the strong force is described by SU3, which is like a rotation of a 3x3 complex unitary matrix, basically SU3. And then weak force is described by SU2. So can we come up with a larger group SU5, which contains both SU3 and SU2? So if you think SU5 as in its fundamental representation, it corresponds to rotation like a 5x5 unitary matrix. Then it contains the upper 3x3 part and the lower 2x2 part, which can be considered as its SU3 and SU2 subgroups. So there is a larger group which can contain the SU3 times SU2 left. So that if that you unify that into SU5, then the gauge group is reduced to SU5 cross U1, and this U1 corresponds to this U1x charge basically. And then the group, you can call it U5 gauge group after you quotient a Z5 group that is shared between SU5 and U1. And this there's an advantage of this model U5 Grand Unified theory, which is also called the Georgi-Glashow model, that the neutrino, that this stereo neutrino stand out as a trivial representation. So it can be included or excluded from the model then. So it does not require the stereo neutrino to be presented in this model. And regarding this notation, one may, some of you may notice that I have some very strange notation here. It is because the way that this U1 group and the SU5 group shares a Z5 common group, there's two different, there's actually, I think 4 different non-trivial ways, but 2 different classes. So the idea is that when I put the label K here, so what I mean is that there is a short exact sequence such that this U5 group factors to SU5, and then there's this U1, and this U1 basically corresponds to the to this U1 here. But when you start from the U5 group and take the determinant, you can identify the determinant of this 5x5 unitary matrix as with this U1 by quotienting some Z5K subgroups of the U1, meaning that it basically means that if you perform a unit, so this SU5 has a Z5 center, and the Z5 center, if you take the generator of the Z5 center that performs a 5-fold rotation of the 5 in its fundamental representation as a e to the I pi I2 pi over 5 times identity matrix. The question is, how do we identify that generator of the Z5 center with a group element in U1? So there can be different ways. And then this U1, you can also think if U1 is a 2 pi rotation as a whole, then you can also partition it into a Z5 group. There's a Z5 group in that. So do you identify the generator of this Z5 center with the generator here, or with 2-fold of the generator here, or with 3-fold of the generator here? Then that's different identification correspond to the different numbers here. It's a very subtle point, but it turns out that if you choose the conventional way of doing this identification, that is to identify the Z5 center generator with the 1-fold generator in this Z5 subgroup of U1, then it turns out that kind of identification does not allow this combined U5 group to be embedded in spin 10. Well, spin 10 is a larger gauge group that we'll mention in as a gauge group of a SO10 Grand Unified theory later. So in order for all the story to consistently be embedded in SO10 into this SO10 Grand Unified theory, or embedded in spin 10 group, basically the U5 group we need to specify here has this very subtle identification. Okay, so that's a very subtle thing, but finally there is another one can say it's an all-encompassing gauge group, which yeah.
Can you comment?
Sure.
Can I comment one thing? Just the previous one. I think I want to point out that in the previous literature, people wasn't so careful about the global structure of the D group. Usually, they just think, in certain cases, they probably will say Lie group, but a lot of time they only check the Lie algebra level. So in a sense, they may just say, oh, this group is SU5, and this group might be just U5, but they don't really imply the global Lie group U5, but they just mean SU5 Lie algebra times U1 Lie algebra. So this fact of U5 with this sub index that we call some 1, 2, 3, 4, and 0, this index, as Yi-Zhuang just say that there are two class and one trivial class. 0 is the SU5 times U1. If we denote U5 0 is the U5 0 is SU5 times U1, and U5 2 is one of them that we study, and there's another one that's the U5 1. So this index wasn't really being introduced, I think, until we really think about this problem more carefully. And I don't think in the high energy literature, at least in the phenol side, there wasn't really point out this fact. Yeah, and this fact actually bothered us for maybe a month because we were wondering, say, how the overall global structure of this Lie group really compatible. It turns out that they have some subtle fact that they didn't point out in the past, and I think it's something we kind of figure out in the paper. Okay.
Right.
Thanks.
Yeah.
Question. How can we determine there are two non-trivial identifications?
I mean, there are non-trivial representations labeled by this integer k, but if k goes to k equals 5 is the same as k equals 0, so you can enumerate all possible identifications. So go from k equals 0, 1, 2, 3, 4. Basically, that's all the possibilities. But you can look into this further and try to not identify, but equivalent some of them. And then so the only interesting one that or the only relevant one we want to look at basically is U5.1 and U5.2. U5.3 is basically equivalent to U5.2, and U5.4 is equivalent to U5.1, and U5.0 is basically not a U5 group. U5.0 is SU5, just direct product with U1. Yeah.
I see.
So that's all the possibilities. Yeah. But I think our contribution is we figure out that this U5.2 is what should be used here. And in this U5 representation, basically, you can label all the quarks by their SU5 representations, and it turns out the representation are arranged in such a way it has a representation 5 bar, 10, and 1. And then the idea of this identification 2 is basically the 5 bar representation carries this U1x charge -3. So you can also understand this identification on the representation level, that this 5 bar does not, as usual, you may think, okay, fundamental representation, maybe 5 bar carries -1 charge, but that's not the case here. It's carries -3 charge, not -1. So that's also that also reflects the subtleties, how you combine this U1x with SU5. How you identify their representation together. Okay, so that's another way to try to unify gauge forces, for example, strong and weak forces. And then there's a larger group which unifies all the forces, and also all the fermions, and then all the 16 fermions in each generation is all unified as the 16 representation of SO10 or of spin 10. So that's the largest gauge group we can consider.
Let me comment one thing.
Yeah, sure.
Sorry for that. I think also it's great to have people ask questions. I think one thing I think Da-Chong maybe pronounced correctly, and also Yi-Zhuang answer is that the identification that between this U5.2 and U5.3 is based on some relabeling of the charged object under the representation. If you have some way to relabel them and then identify, re-identify the objects in some way, then they should be the same Lie group. but it turns out they are just two class. And another thing I think I want to point out is that this type of a table certainly should be well known in people who are careful about representation, but a lot of time when you read from maybe Wikipedia, they will just mix up the particle, the way to count the particle. I think here Yi-Zhuang present is that every disk, a small disk with some colors, the disk is actually a Weyl spinners of some space-time representation of the spin group, which is a two-component doublet of the Weyl fermion. And this way of counting will not have ambiguity of counting degree freedoms, as what maybe you can go to the Wikipedia, you will check the standard model present is kind of not confusing what exactly is the particle and how many particles they are. That may be confusing, but if you count this way, I think it's much better and clear, and it's more mathematically precise.
Yeah.
Based on counting this Weyl spinner of the space-time representation with spin group, spin 3,1 in the Lorentzian, or spin 4 in the Euclidean, but the doublet, two left-handed. So, yeah, thanks.
Yeah. Okay, so so let me summarize a little bit. So basically, what we have just introduced is that we have a standard model which has a I'm not using Lie group, I'm using Lie algebra, so which has this gauge algebra, let's say, and then we have the Georgi-Glashow model, which has U5 the algebra, and then the Pati-Salam model is the algebra is SO6 plus SO4, and the largest one is the SO10 Grand Unified theory. So all these SO10, Georgi-Glashow and Pati-Salam, they are well-known models of Grand Unified theory on top of the standard model. So we can try to understand how the gauge forces are unified in these models. So we can maybe start from the largest algebra, and we can make a plot like this. So in this plot, every dot corresponds to a gauge boson in the SO10, let's say, gauge theory, or actually it has a Lie algebra. More precisely, each one corresponds to a Lie algebra generator of SO10. And then that's basically all the forces you can have. And then I'm drawing each subgroup, and every subgroup actually is generated by a sub-algebra, which only pick part of the generators. So for example, U5 is this one, and then that's the forces in the Pati-Salam. Sorry, that's the forces in the Georgi-Glashow model. And then this Pati-Salam correspond to SU2 left cross SU2 left cross SU2 right, and cross this SU4, which is also on the algebra level is also same as SO6, which is this yellow one. So, and then finally the smallest one is the standard model, which only contains the SU2 left, which is this one, and SU3. And then two of the two U1s. One is the hypercharge, the other is this so-called X charge. Okay, so you can see how forces are unified gradually by originally in the standard model we have these red particle, this red part correspond to the 8 gluons that we know that mediates the strong force, and these 3 basically is the particles that mediates weak force, and then there's also particles which is correspond to photons mediate the electromagnetic force. So by basically combining them into, for example, a larger gauge group or a larger algebra, basically you are unifying these gluon or force mediators together such that these gauge bosons no longer are distinct. They can be unified in this way gradually. But there's miraculously, there are interesting observations. So first of all, we notice that if you take the Georgi-Glashow Lie algebra, and then the Pati-Salam GPS, if you try to look at the intersection, so the intersection, if you look at this blue blue square, basically. How does it intersect with these two green and orange and then yellow squares? And then you can see that their intersection is only this one, and then this orange, and then this red. So that precisely corresponds to the algebra of the standard model. So the intersection of these two algebras give rise to the standard model algebra, meaning that the standard model, all the gauge forces in the standard model are the common gauge forces that can be mediated, that exist in both the Georgi-Glashow and Pati-Salam models. So this is a very interesting fact. Usually it can be greater equal, right? It's a smaller algebra. It just need to be contained in both of them. But it turns out that it actually not only is contained in both of them, but it corresponds to the intersection of these two. So that means there are some very precise relations somehow between them to give rise to this interesting result. Another result is that if you try not to do the intersection, but to do the union, if you combine these Lie algebras together, of course, combining the Lie algebra is not only you just treat them as a set and combine, but you also need to complete all the Lie commutators between the generators, such that it will usually lead to a larger Lie algebra. And it turns out this kind of a union just precisely give the SO10. So this hints that there are some very rigid relations between all these Lie groups that people discuss in grand unified theory. That's also one motivation that motivates us to explore the relations between them. So the standard model is the conclusion. Standard model is the intersection of these two grand unified theories in this sense. So the goal is try to understand. Maybe there can be phase transitions between all these different theories. So starting from the largest gauge group, try to break this. So I want to make a comment is that we can try to treat all these, engage all these gauge group and treat them as symmetries for now. And then instead of saying it's all Higgs transition of gauge theories, we can also think of it as symmetry breaking transitions from a fermion theory with a larger symmetry to these Weyl fermions, which has smaller symmetries. So we want to understand the structure of these group structures and try to understand how symmetry transitions occurs.
By the way, excuse me, one minor comment. I think you Yi-Zhuang say nicely about the intersection between GGA and PS is a standard model, but this one actually contains a slightly extra one, which you also write the U1X. That may or may not be included in the usual standard model, but I think if you care about baryon minus lepton, you will include that U1. But in any case, what is written on the side are clear. I just point out in case. There's one more U1 in this GSM defined here.
Yes, yes.
Thanks.
Okay, so in order to understand that, basically, and by understanding, I mean, try to write down the precise Higgs field. For example, what do I need to do if I want to start from a theory with SO10 or spin 10 symmetry, and then down to all these subgroup? What kind of Higgs field should I condense? So in order trying to find out the Higgs fields that that triggers or that drives all these symmetry breaking transitions or Higgs transitions. So we can basically try to inspect the branching rules. The idea is that suppose I want to start from a larger group, the group of SO10 grand unified theory to the group of PS, Pati-Salam model. Then if I want to break the symmetry from a larger group to a smaller group, then I want to condense something which is a non-trivial representation of the larger group, such that by condensing that Higgs field, you can break the larger group. But the Higgs field must also belong to the trivial representation of the smaller group, because after condensing the Higgs field, you want to bring the larger group to the smaller group, not further break it down further. So the Higgs field must transform trivially in this smaller group. So we can try to look up the tables of this group theory representation branching rules and try to find the appropriate representations in this SO10 group basically, and which can branch to a trivial to some basically to direct product of representations which contains a trivial representation in terms of the smaller group. So what we found is that, for example, of course, the choice is not unique, but one possibility that we found, and we think it's interesting probability, is that the 54 representation in SO10 basically can branch to a trivial representation in PS. So that indicates that we can create, we can write down a Higgs field which belongs to this representation, and if we condense this Higgs field in an appropriate manner, such that the expectation value of the Higgs field transforms as a trivial representation in this group, then that kind of condensation will break this larger group to the smaller group. And we can further ask, how can we further break this PS to the standard model? And then that's the same idea. Then you need to find some non-trivial representation in PS, which transform trivially in this standard model gauge group. So, so there's another options. For example, you can do this kind of Higgs condensing, but it turns out this can also originated from another representation 45 in SO10. And there's another way of doing this symmetry breaking exercise, such that we start from the largest SO10 and go through the other paths through the GG and then to the standard model. But if we want to do that, again, if we do this exercise, then we try to find a representation which is non-trivial in the larger group, but it branches to a trivial representation in the smaller group. And then one option is the 45. And then if you further along this path want to break it to the standard model, then what we found is that you can try to do this. Try to condense the 24 sub-zero, because this GG is SU5 cross U1. So this is the SU5 representation, this U1 representation. And then you can do this. And then this also has an interpretation in terms of SO10, which basically because the 54 representation in SO10 can generate the 24 in this GG group. So it seems that all the symmetry breaking pattern all has to do with two representations and only two representations in SO10 nicely, that if you first condense the 54 representation, you can bring the largest SO10 grand unified theory to PS. And then if you further condense 45 in this way, you can further break it down to standard model. But if you first condense 45, you will bring it to GG. But if you further condense 54, you will further break GG to the standard model. So it turns out that only we basically need to specify two Higgs fields are identified. They transform as the 54 and 45 representation of spin 10. So the story basically is that we introduce two scalar fields. And these scalar fields, basically they correspond to the Higgs fields. And then they transform as the 45 and 54 representation of spin 10 or SO10. That's actually the same meaning. And then in order to understand what they correspond to, so 54 and 45 are the dimension of this representation. But what kind of object in SO10 representation has that dimension? Well, it's easy to see that the anti-symmetric, this 45, actually, the meaning is the anti-symmetric rank 2 tensor representation of SO10, which you can think SO10 as a 10 by transform a rank 2 tensor, which means it's like a 10 by 10 matrix. But if this matrix is an anti-symmetric matrix, then the independent matrix element is 45. But if it is a symmetric matrix of 10 by 10, the matrix element number of independent elements is 54, basically. So they actually just correspond to the anti-symmetric and, sorry, I should also say traceless, and anti-symmetric and traceless symmetric rank 2 tensors of SO10. So if you write down certain Higgs fields, which takes this form and transform in this way under SO10, then we can try to condense them, introduce them to our to the largest theory. And then if we first condense 45 and then condense 54, we will go through the symmetry breaking path like this. If we first condense 54 and then condense 45, we will go through another symmetry breaking path. And this also explains why the intersection of GG and PS is precisely the standard model, because the standard model is the result of breaking both of the breaking the symmetry by both of the Higgs field. So you turn on both of them. So then if you turn on both of them, of course, you obtain the intersection of these two Lie algebras, which turns out to be the to match our previous understanding of which is the standard model Lie algebra. And then another thing I want to mention is that since we have already mentioned this rank 2 tensor representation of SO10, so we know that SO10 rank 2 tensor representation, the total dimension is 10 by 10 because it's like a 10 by 10 matrix, right? Altogether have 100 elements. So 54 and 45 only make up of only make up 99 of these matrix element. There's also one independent degrees of freedom, which correspond to the trace 4, which basically correspond to the identity matrix of 10 by 10, which is the trivial representation of SO10. So this motivates us to maybe think of these two Higgs field. When we think about this Higgs field, we can actually think of them as bivectors. So these are bivectors of SO10 or rank 2 tensors, basically. And then these bivectors of SO10 can further be considered as, because each SO10 vector can be constructed from two SO10 spinors, or more precisely, which is the 16 representation in spin 10. And then the 16 representation in spin 10 is nothing but the fundamental fermions, right? But the leptons and quarks, these fermions transform as a 16 representation. So that indicates that we can use this, another way try to understand how this Higgs field is originated from is to think that we start from these fundamental fermions, and if we combine two of them together from spinor representation to vector, and then we further combine two vector, which is 4 fermions, and these 4 fermion terms or 4 fermion operators can correspond to these Higgs fields. So these Higgs fields are unusual because in the usual context of Higgs field usually correspond to certain fermion bilinear. We are condensing, when we condense a Higgs field in many contexts, usually we consider fermion bilinear condensation, which may create a mass for the fermions. But here, the Higgs fields that we condense in this diagram all correspond to 4 fermion operators. So they do not immediately give rise to a bilinear mass for the fundamental fermions. Instead, they introduce interactions to these fundamental fermions. So, okay, with that knowledge in mind, we can try to write down the full theory, which of course still involve the Yang-Mills term, where we have 16 these Weyl fermions, which transform as the 16 representation of a spin 10, which couples to the gauge field. And then we also can write down a Yukawa-Higgs term, which describe how these fermions couple to the Higgs fields. So the Higgs field that we introduce is written in terms of this capital phi. It can have its own dynamics, and it can also have its quadratic term, or even higher order terms. Basically, all these terms correspond to the Higgs potential. And then it's possible to tune the Higgs potential in some way such that you can drive certain representation of the Higgs field to condense or not condense. So that will drive the phase transition. But this Higgs field, because it is basically should couple to the 4 fermion operator. So one convenient way to write down this Higgs field, how it couples to the fermion, is to consider, first of all, you couple this Higgs field with 2 auxiliary fields. So this little phi is some 10 representation of spin 10, which is introduced as an auxiliary scalar field as a Lagrangian multiplier, which further couple to the fermion bilinear. So this is how the fermions, the 16 representation, the spinor representation fermions, how they form the vector representation by contracting their flavors with the gamma, with appropriate gamma matrices. So there will be 10 components of these auxiliary scalar fields. And then if you can further combine this little phi field is already SO10 vectors. You can further combine them into bivectors that couples to the capital phi, and then the capital phi will be the in the desired representation that we want for the Higgs field. So if you try to integrate out these smaller auxiliary scalar field, then you can pretty much see that this capital phi directly couples to 4 fermion operators. So that is how the Higgs field talks to fermions. Of course, the Higgs field, some of this component also transform non-trivially under the gauge group. So the gauge group here, the largest one we consider is spin 10. So of course, you should also couple the gauge field in principle to the Higgs field. But here we are all treating all these gauge field as background gauge field for now, such that we can reformulate the problem as a symmetry breaking problem. So if we condense some of these Higgs field, it will, first of all, the number one effect is to break the symmetry from the larger group to the smaller group. The second effect is to introduce interactions to these fermions, but it will not immediately gap out the fermions, not as the conventional Higgs mechanisms in the standard model. Okay, so we can, with this model, basically we can come up with a phase diagram which describes all the possible condensations of the Higgs field. So altogether, the 10 by 10 bivector Higgs field contains all these 3 different representations, and each representation can be separately tuned to condense. So if we try to condense, let's start from the SO10 grand unified theory, which has the full SO10 or spin 10 symmetry, to be more precise, then if we condense the 45 representation by tuning this quadratic coefficient in front of the Higgs field, if we tune that to the negative side, this R45 is the coefficient in front of this 545 square. So a negative R45 coefficient will try to drive 545 to condense, so that will not be 0. Then that will break the symmetry down to GG. The other path, if you tune 54, it will tune to PS. And then if both of these 2 R's are negative, or another way of saying is both of the Higgs field condense, we end up with a standard model. So that's how all these grand unified theories, as well as standard model, can be arranged all together within the same phase diagram. But there's another option that you can also try to condense this phi1, the trivial representation of the bivector Higgs field. And then if you try to tune that condensation by driving R1 to negative, then you may have another phi1 condensed phase. Perturbatively, you may think, oh, well, in that phase, you just turn on another 4 fermion interaction. So perturbatively doesn't matter. So fermion is not immediately gap out if you turn on this Higgs condensation, because all the fermion interaction, 4 fermion interactions are irrelevant, perturbatively irrelevant in 3+1D, basically, for 3+1D Weyl fermions. But there can be non-perturbative effect, which is beyond this simple dimension counting argument. Actually, this phi1 term, if you inspect it more carefully, it precisely corresponds to the symmetric mass generation interaction that was previously proposed in Xiaogan's paper, and then which is considered to be a dangerously irrelevant perturbation, meaning that if you drive it strong enough, if it is not a perturbation, but it is a strong enough interaction, then the interaction can drive all the 16 fermion to the trivial gap phase without breaking the symmetry. So that's another layer of the story. So we imagine that if we have a large enough condensation of this phi1, you can also enter a symmetric mass generation phase where all the fermions are gapped. So it turns out that this is a very rich phase diagram, that many interesting phases and physics all happens in the same phase diagram just by tuning the Higgs potential in different ways. So that's basically the first part of the story. Juven, you have a comment?
A comment about the comparison to Xiaogang Wen's work is that I think the way he ate the interaction are particular one type of interactions from 4 fermion, as you say. But I think we may get extra terms that he doesn't have. I think that's basically there's still some different.
Yeah.
But he contained one term we had, but I'm not exactly sure. Yeah, maybe can discuss.
Okay.
There could be different effects. What are the terms that can be added to drive to SMG, symmetry mass generation?
That's right. So the point is that this phi1 term is only one possibility to drive to SMG, but not the unique one possibility. Yeah. Okay, so this phase diagram pretty much reminds us the phenomenon of deconfined quantum critical point in quantum magnets, which is very familiar to many condensed matter theorists. Well, this is a system proposed, I think in 2000, around 2004, something like that. And then it's believe that in the square lattice 2 plus 1D quantum magnet, there are two different phases. You can either be in the antiferromagnetic neo phase or VBS phase, and these two different phases breaks two different symmetries. And one breaks for example, the spin rotation symmetry, and also the other breaks this C4 rotation symmetry of the lattice. So these two distinct symmetry breaking phases somehow can join at the same point, transition from one to another through a direct continuous transition through a quantum critical point. That's the scenario there. So one may look at this phase diagram. Okay, then there's a symmetric phase, which is this SO10 GUT. There are two different distinct symmetry breaking patterns by condensing two different order parameters, which just like neo and VBS, they correspond to two different order parameters as 45 and 54 here. So the question is there a similar story there, that we can also have a continuous direct transition between GG and PS, just as what happens in the deconfined quantum criticality between neo and VBS. So in order to explore, so this motivates us to explore further this idea, whether we can drive a DQCP between these two, let's say, symmetry breaking phases. And then the key mechanism for deconfined critical point or deconfined quantum criticality is that there's a requirement, or there's an important feature between the order parameters of the two distinct symmetry breaking phases, that the topological defect of one order parameter, let's say the neo order parameter, must carry the charge of another order parameter, for example, the VBS order parameter. And it's also the same idea, vice versa, that the defect of VBS order parameter also carries the charge of the neo order parameter. So there is a mutual defect and charge capturing each other. So that's why when you try to condense the defect of one order parameter, try to disorder the phase, then you also, by doing that, you also condense the order parameter of another phase, so that also drive you directly into the other phase. So that's one key mechanism underlying DQCP. So in order to realize that, we need to introduce some this so-called intertwine order, some intertwinement between these two representations of the Higgs field, such that under that circumstance, maybe the defect of 45 will carry the charge of 54 and vice versa. If we can realize that kind of locking between the defect and charge, then this mutual locking basically, then probably we can also realize the similar physics as the deconfined quantum critical point. However, in order to understand that kind of a locking, very importantly, we need to understand what are the possible topological defects of this Higgs field at the first place, right? Because if you don't know the defect, you don't know how to even bind the charge to the defect. So in order to understand the defects of certain order parameters, symmetry breaking order parameters, well, that's a very well-established field in condensed matter. That's all these order parameters is always described by the larger group quotient the smaller group. If this order parameter correspond to the order parameter that breaks the symmetry from the larger to the smaller group, then it lives in a manifold, which is described by this quotient, by this coset space, basically. And then, so that's where the 45 and 54 lives in, because they all correspond to the SO10. The larger group is SO10. Here, I don't mention spin 10 because we're already focusing on the Higgs sector, where it's all bosonic. It has nothing to do with also all those 16 representation of spinor fermions. So we may as well consider the largest group as the SO10. No problem for this discussion. So this is the manifold of these two order parameters. And then we notice that they have non-trivial homotopy groups in 2 dimensions. So the pi2 of this manifold and pi2 of this manifold, it turns out to be non-trivial. This one is Z, this one is Z2. So what does it mean by pi2? So remember, all these Higgs field, they live in a 3+1 dimensional space-time. So the space dimension is 3. So in the 3-dimensional space, this pi2, non-zero pi2 means that we can consider that there's a monopole, such that the monopole is surrounded by a 2-sphere. And then on the 2-sphere, if you have a non-trivial map of this non-trivial arrangement of this order parameter that falls into a non-trivial classification of this homotopy group, then this kind of field configuration surrounding that 2-sphere indicates that in the core, in the center of this sphere, there should be a monopole. And that kind of monopole is classified by the same classification of this pi2, which is Z. So that indicates that this 45 representation of the Higgs field has a Z classified monopole in 3-dimensional space, and 54 has a Z2 classified monopole in 3-dimensional space. So at least we identify 2 point defects. One is made of 54. One is a topological point topological defect of 45 Higgs field, and then another is also a point defect of 54. And the idea is that we wish that these 2 point defect, as you may think of them as particles in 3-dimensional space, can have non-trivial braidings between these 2 monopoles. So the requirement for this defect to trap the charge of one each other basically boils down to this non-trivial braiding of these 2 different monopoles. So they should behave as monopoles and charge in with respect to each other mutually in 3-dimensional, in this 3+1 dimensional system. And more precisely, this
comment,
yeah,
if I can, because I think some people might be confused about the name monopole. Here, the monopole here we discussed is not a monopole or magnetic monopole in the gauge theory, like a U1 in the standard model or U5 gauge group. We are not considered a monopole for that type. We'll consider the topological defects, Yi-Zhuang You monopole, but for the Grand Unified Higgs field, Grand Unified series.
Right,
Higgs
right.
Field,
It's a
Higgs
defect
field.
of the
So it's
scalar field.
Right. So it's the monopole in the topological defect in the scalar fields of the God Higgs, but not the monopole in the gauge sector of the U5 sector. It's different type of
Right, right. It's not a defect in the gauge field. It's a defect in the scalar Higgs field. Yeah.
Yes. Thanks very much.
So that's what the monopole or the point defect we are talking about. And then there are, and as we said, there are 2 different point defects. Each correspond to the defect of each of the order parameters or Higgs fields that we try to condense. And more precisely, this mutual braiding between these 2 types of defects can be understood. Basically, if you want to formulate them more precisely, we should not restrict ourselves to the 4-dimensional space-time. Instead, we need to extend into the 5-dimensional space-time in order to formulate this braiding effect more precisely. So let's imagine that these reds, these 2 monopole correspond to the red point and the blue point. And then in the space-time, in the space, they are point defect, but in the space-time, they correspond to a word line. So this may be a word line of a first type of the 40, let's just call it 45 monopole. And then this is the word line of the 54 monopole. And then if we extend the dimension, space-time dimension, to one additional auxiliary dimension, all this word line of the monopole will expand it into a word sheet. And then this so-called monopole mutual braiding is precisely described by the effect or by the phenomenon that the 2 link the word sheet in 5-dimensional this space basically give rise to a -1 sign. So that's what we mean by this non-trivial braiding between these two monopoles. So of course, this drawing, I can't really draw a 5-dimensional space, so it's all don't take it too seriously, but it's all only for illustrative purpose. But mathematically, one can figure out that precisely in 5-dimensional space, 2-dimensional manifolds can link with each other, just as in 3-dimensional space, 1-dimensional loops can link with each other. That's almost the same idea. And then this non-trivial linking between the pseudo worldsheets of the two types of the monopole is the key. Then, but in our original theory, when we introduced the Higgs field, we didn't include this effect to the Higgs field. So in order to include this effect, we need to add one more term to our Higgs theory. And that term is a Wess-Zumino-Witten term, or you may say the Wess-Zumino-Witten-like term. It looks like a Wess-Zumino-Witten term that assigns a -1 sign to every linked pair of monopole pseudo worldsheets. And this term can be written in this way, that it can be formulated as a so the way to think of this is like it's almost like a BDC theory. If you want to think of this B and C as two-form, some two-form fields that you can try to define. And then the B and C actually correspond to the generators of the second cohomology of these fields with Z and Z2 coefficient. Why do I want to do that? Because the point is that you want this B and C to count these monopole numbers, and the way to count the monopole numbers or monopole current is by trying to come up with a two-form field which belongs to this cohomology, such that when you integrate the two-form field on a two-manifold, it will precisely give you the topological index of this non-trivial map that matches the pi2 classification. So this B should correspond to the Hom group from the result of this pi2 to Z, and or from this, the other C should correspond to the mapping from this pi2 to Z2, which basically maps the non-trivial arrangement of your Higgs field to the topological index, basically either Z or Z2. So this is the B and C. So they are basically the two-form field that counts the non-trivial topological index. So if you try to describe the linking between them, then that can be described on the field theory level as a BDC theory in the 5-dimensional extended space. So that's, of course, an extension of our 4-dimensional space-time, such that the 4-dimensional space-time is basically the boundary of this 5-dimensional extended theory. So that's the way to formulate.
Comment.
Yeah. Okay.
The figure, I think we can replace this worldsheet, 2D worldsheet, the red one and the blue one. Both are 2D worldsheet to something like maybe 2 spheres. In 5 dimension, the two of the 2 spheres can be linked. And one way to count is that you can fill one of the 2 spheres with a 3-dimensional ball, such that the two sphere, one of 2 sphere, which are not filled, and another 2 sphere which is filled with 3 balls. They have an intersecting number 1, and then there will be the intersection that also corresponding to the linking invariant.
Yeah.
But the difference here, I think also Yi-Zhuang mentions that these are WZW-like term, but the difference is that the usual WZW term, I think, is more like a Z class, which means the link invariant you might be able to detect maybe also a Z class type of theory, but in our case, we only have a Z2. And so these are the discrete Z2 or Ma2 class, which Yi-Zhuang will explain next, I think. Yeah, that's all. These are different from the usual way.
Yeah, it's a different one because it's also natural because one of the monopole is only Z2 classified, so you don't expect a Z coefficient there. Okay, so basically the full theory that we are proposing contains the Yamiya's term and the Yukawa Higgs term and this Wess-Zumino-Witten term that assigns non-trivial braidings to the monopoles of the two different Higgs fields. And then the whole theory in the presence of this Wess-Zumino-Witten term actually has a SO10 T-Hoof anomaly captured by a 5-dimensional bulk invertible TQFT, which is this is the anomaly polynomial correspond to the matching this theory. So this anomaly, I want to comment that it purely originates from the Higgs sector. It's all because we add this Wess-Zumino-Witten term to the Higgs field, such that the Higgs field can be viewed as in this sense, Higgs field basically is tuned to the states, which it can be viewed to as a 4-dimensional boundary mode of a 5-dimensional bulk SPT state. So we are actually considering there's nothing strange happened to the fermion, but when we try to couple the theory to the Higgs field, this Higgs field is not a usual scalar boson living purely in 4-dimensional space-time, but it actually is coming from some boundary modes of a 5-dimensional bosonic SPT states, such that it has this anomaly on the 4-dimensional space-time, which is on the boundary of these SPT states. And that is, it turns out this SO10 SPT state is just Z2 classified. We're just choosing the non-trivial class there. And then because of this anomaly, the SO10 or the spin 10 cannot be gauged on the 4-dimensional boundary alone, but it must propagate. Once this group is gauged, in the gauge field must propagate into the 5-dimensional bulk as well. So another. Yeah.
Maybe comment. I think let me clarify a few things. First, just for the audience, here W2, W3 are second and third Stiefel-Winnie class. And this class here written in the slide is V of SO10, means some W2 of a Stiefel-Winnie class of an associate vector bundle of SO10. I want to clarify this one is actually also as a constraint, such this term is constrained to be the same as the W2, W3 of the space-time bundle. So which means this written on the slide is actually means that there's some gauge probe, which you can call anomaly of a gauge type. But the other one, which this term is actually equal to W2, W3 of tangent space-time tangent bundle Tn, which means there's also gravitational probe. So this anomaly actually is a mixed gauge and gravitational anomaly. And this anomaly, although looks very similar to the one that you might be reading from fermion electron dynamics, but somehow in my more strict and rigorous opinion, I think they are still different because this is actually mixed gauge gravity anomaly, while the fermion electron dynamics actually is a pure gravitational anomaly. Another way for expert who might be watching on YouTube or reading this lecture or video later, I'll just say the original W2, W3 of a gravitational anomaly can be trivialized by pullback from SO, the space-time symmetry group SO, spatial orthogonal group, to spin C, which is spin times U1 mod Z2. While in this case, this anomaly is actually exists in spin of space-time symmetry group times spin 10, a model Z2. This anomaly still persists there in spin times spin 10 mod Z2. And that's a different. The spin C one actually, spin C, which means spin times U1 mod Z2, that's the one that people consider the fermion dynamics. That one is a pure gravitational anomaly, trivialized in the spin C structure. This one is a mixed gauge gravitational anomaly, which persists, still exists, maintains there in the spin times spin 10 mod Z2. So the whole anomaly here is actually a mixed gauge gravitational type, mixed between the space-time spin group and the spin 10 of the gauge group, mod Z2. And of course, here we consider the whole anomaly because the spin 10 is treated as a global symmetry, not yet dynamical gauge. And the last comment about once spin or SO10, spin 10 precisely to be gauged, cannot be gauged alone on 4D, but need to gauge also in 5D. So that's why the gauge field propagate to 5D bulk. And thanks, Yi-Zhuang, please.
Right. And another thing is that this W2, W3 anomaly is lifted if this spin 10 group is broken down to its subgroup. So the subgroup of interest in our discussion, of course, is the subgroup correspond to GG, PS, and SM. And in these subgroups, there's no longer this anomaly. So, so that means if we condense either 45 or 54, it will break the spin 10 symmetry and removes the anomaly. So the resulting Higgs resulting phase is just the Higgs order phase, just the symmetry breaking phases. And then the anomaly only exists in the symmetric phase, which is the this SO10 gut, and also along the phase transition. For example, along this line where the symmetry, the full SO10 or spin 10 symmetries is restored. But due to the anomaly, which means if you enters the symmetric phase or on the transition line, then the Higgs field cannot be trivially disordered or gapped because of this anomaly. So the order phase is not too different from the conventional order phase, but the disorder phase will be very different. And this transition line will also be different. It will be modified due to the anomaly. And one possibility is that the Higgs field, the anomaly is saturated as by a gapless theory, that the Higgs field enters or even by certain topological order in some sense, that the Higgs field enters a spin liquid phase, a fractionalized phase, when the full SO10 or spin 10 symmetry is restored. So so this may happen either along the transition line and also in the SO10 symmetric phase. So so the last thing I want to mention a bit more about is this spin liquid phase. So we also try to look into what kind of possible spin liquid or fractionalized phase or deconfined phase that can arise to match the W2, W3 anomaly we just mentioned. And then that's basically the question is, how can we use another theory which may contain fractionalized degrees of freedom to match the anomaly that was introduced by the Wess-Zumino-Witten term that we just write down for the Higgs field. So one possibility, of course, we didn't enumerate all possibilities. So one possibility that we'll provide in our paper is basically a QED theory, a QED4 theory, which contains some fermions, which couples to an emergent internal gauge field. And then it also couples to the 45 and 54 Higgs field in a bilinear manner. So these fermions are not the fundamental fermion in the standard model, because we know that those fundamental fermions were coupled to the Higgs field in a quartic, in a basically 4 fermion manner, but here is a 2 fermion bilinear manner. So that's the fractionalization of the Higgs field. So the idea is that you can fractionalize this bosonic Higgs field into a bilinear of some, sorry, this should be Cauchy, not phi. So should to the fermion bilinears, and then they correspond to these bilinear mass terms of the Cauchy fermion. And Cauchy transform as 10 in SO10. They are the fermionic partons, and they are 10 Dirac fermions, not Weyl fermions. And each carries 1 unit of the emergent gauge charge. And here the gauge group, it turns out that this theory, including these mass terms together, the largest group that you can gauge is U1. And then I put a prime here in order to indicate that this U1 gauge group has nothing to do with any of the U1 group that ever appeared in the standard model or in the previous discussion. So this is a completely new U1 gauge group, which comes from the fractionalization of the Higgs field, of the GUT Higgs field. And that's the so-called emergent U1. And of course, there's a gauge boson that mediates this U1, which is this denoted as this little a gauge field, which is neutral under SO10, but acts as a U1 gauge field that combines these 2 fractionalized fermionic partons together. And that is what we also call the dark photon. And the word dark means that this photon has no coupling with any of the standard model particles. It only talks to these fractionalized fermionic partons. And then the fermionic parton basically were introduced in order to represent the original Higgs field, which is SO10 bivector. And then the fractionalization scheme is like this. So how do we know that this parton theory, which is formulated as a QED theory, has the same anomaly as the Wess-Zumino-Witten theory that we just written there? Well, one way to check is that we can try to do an anomaly matching exercise, try to figure out what's the anomaly of this fermion theory. So for the sake of checking the anomaly, one can for temporarily turn off all these Higgs fields, and then one can focus on this fermion theory. And the fermion theory in this case, 10 Dirac fermion without the mass turn, basically you can reformulate it as 20 Weyl fermions. And these 20 Weyl fermions, you can think of it as 2 times 10, which transform these 2. It's like a 1 Dirac equals 2 Weyl. This 2 has an emergent, has an enlarged SU2 structure. And then this U1 gauge is just a subgroup of this SU2 prime. So you can consider this 20 fermion as in the SU2 times SO10 representation. So the fermion is already vector representation in 10 of SO10, but also this Weyl fermion also contains the SU2 prime internal symmetry as well. So that's totally 20 Weyl. And then you can further embed this group into SP10. Well, SP10 is the symplectic group of 10 dimension, which is basically the group that rotates 10 quaternion numbers. So the way to embed this group into this group is to think if you rotate 10 quaternion numbers, instead of you can do a quaternion rotation for each components of these quaternion numbers, you can separate out a global rotation of the quaternion numbers, which is SU2, but the remaining rotation you can only do SO10 rotation for the 10 component because they looks basically like real components. So that's the embedding, but this embedding means that precisely the same theory has another way of thinking, that SP10, which is the group that rotates 10 quaternion numbers, can be splitted into the group that rotates the first 2 quaternion number and the last 8 quaternion numbers. So that's SP2 and SP10, SP8. And then this SP2 actually is in a, you can show that the fermion will be branched into a 4-dimensional representation. But SP2 is also the same as SU2, and this SU2 is different from this SU2. This is another embedding of SU2 in SP2. It's the special embedding, which correspond to, well, the fermion transform again as 4 in this SU2. And why do we want to go through all these subtleties? Because we can then use the conclusion that's coming from the new SU2 anomaly, that the statement is that if there's some Weyl fermions which transform as the representation 4, in representation 4 basically means spin 3/2 in SU2, then these fermions will generate the W2, W3 anomaly. And through similar argument, we can also check that this does not generate W2, W3 anomaly. So this means that this theory has a W2, W3 anomaly, so as this one, so as this one, and so as this one. But here, this U1 part doesn't contain the W2, W3 anomaly because it can be nicely gauged, and it's coming from the fractionalization of the parton, which is a totally internal gauge field. So the W2, W3 anomaly must enter the SO10 part. So that's through this argument, we basically try to match that, argue that this SO10 rotation of these fermions has the W2, W3 anomaly matching the anomaly that we previously introduced by introducing the Wess-Zumino-Witten term. So the whole argument basically try to say that by introducing this term, there can be the Higgs field basically can admit a parton construction such that it can reproduce all the non-trivial phase factors that is required by the Wess-Zumino-Witten term. But this kind of fractionalization means that there's another way to understand the low energy consequence of this Higgs field, that the Higgs field is in such a liquid phase, such you have some fermionic parton, which is gapless, coupled to the so-called dark U1 gauge field. And then all these fermionic partons altogether 10 components as the vector of SO10, where one can further try to break it down into the representation of all the strong, weak, and hypercharge of the standard model gauge group basically. And then one will immediately find that all these 10 fermions, they transform in this representation as listed in this table. But the point is that you can see some of the fermion only carries the color of SU3 strong interaction. Some of the fermion only carries the isospin of the weak interaction. So this is this basically says why these fermions are special. Because in the standard model fundamental fermion, no matter you are thinking about quarks or leptons, none of them only carry. So basically, they all either carry some strong or some weak. Or the punchline is that at least their charge their charge assignment is very different from these emergent fermions. So these fermions, in terms of this SU3, SU2 charge assignment, there's some kind of color flavor separation that some of the fermion only carries color, some of the fermion only carries the weak isospin. Not only that, these fermions are also not neutral under the U1 dark gauge field. So that's basically the spin liquid phase for the Higgs field. So imagine that our universe, maybe in the early history of universe, it encounters such a phase when it cools down, then such a deconfined critical phase basically can leave some imprints in our current universe, maybe we think. So because in nowadays in our universe, we have already entered the standard model phase, meaning that we are starting from this SO10 symmetric phase by condensing the 542 and 554, by condensing these two Higgs fields. But once these two Higgs fields are condensed, immediately create mass for all these fermionic partons. So we can no longer see these fermionic partons at nowadays energy scale because they are all gap out at the grand unified scales. But something is left over, that is these gauge photons. The gauge photons, U1 photon doesn't automatically confine in 3+1D. So there's a possibility that these dark photons will decouple from the whole this fermionic parton sector. And then because it's also neutral under all the standard model interaction, so it doesn't interact with any of the particles that we can see through the gauge interaction. Maybe the only possible interaction it can talk to us is through gravitational sectors. So it will remain as a dark cosmic background radiation in our universe. So that provides one maybe possible candidate for dark matter in our universe that does not talk to the standard model particles. Okay, so I guess I'm over time. And then thanks for your attention. And then that's it for today. Any questions? Yeah.
Can I ask a question, Yi-Zhuang?
Yes, yes.
You mentioned that our universe has entered this standard model phase at some point. As a function of time, how does one think about this transition? Because it's in the sense that if the Hamiltonian is time independent, right, then that can't occur.
Right, right.
So what's the picture in terms of some?
Yeah, I'm not. Yeah. So here, okay, that's a very good question. So we're on one side, we try to think of all these phases as related by, maybe they can be related even by quantum phase transition, meaning that you may be able to tune some parameter in your Higgs field Hamiltonian to drive this transition even at 0 temperature. But since they are symmetry breaking transition, so they also has some, like they can also has a thermal transition counterparts. So you can also think that these potentials are not tuned by some driving parameter, but by temperature. So maybe that as you cool down, as temperature goes, we may start from some theory here, and then as we lower the temperature, the universe goes through a trajectory that may enters one of the phase and then eventually end up with the standard model phase. So one may think these are also tuned by temperature in some way. But the point is that we don't know yet whether these two Higgs fields, they have this non-trivial mutual monopole braiding or not. So if there is a possibility that there is a non-trivial Wess-Zumino-Witten term between them, then this whole grand unified theory basically will not only contain the fermions that the quarks and leptons that we are familiar with, but also contains a lot of Higgs field, where these Higgs fields are not in the standard disorder phase, but instead in a spin liquid phase. So that means there are also fractionalized particles and gauge photons there. So as the universe cool down very quickly, so you are going through a non-equilibrium process, maybe through all these phases, and then there's no time for everything to reach the ground state. Then some of these non-equilibrium, maybe some of these U1 gauge photons, which were originally in this phase, can still persist in the standard model phase. That's my thoughts. Yeah.
But and if they persist, then are there any experiments one can propose for current?
Yeah, because I don't know. I don't know.
Are there bounds you can put that from current experiment on that? How much you can rule out, or?
Yeah, we haven't checked that yet. We haven't go to that. I think that's a very good question, and that indeed maybe we can put more efforts trying to compare with the current dark matter observations.
Can I ask one more question? Sorry.
Sure.
No worry, I just want to answer Taro. It certainly is a to-do list, but first of all, actually this phases all on the 16 biofermions model. So actually, I also feel like it's possible maybe if we do have a 3 generation at least of 3 families of the biofermions. I doubt that actually all the 3 generation require the 16th biofermion right-hand neutrino. In my previous work, I proposed that some generation right-hand neutrino may not exist by replacing the right-hand neutrino by new sectors of new TQFT, topological field theory, or new conformal field theory, or even gravitational theory with some topological gravity type to saturate some Z16 anomaly. If you were in my talk, then the question you ask certainly is very nice to explore the experimental evidence or consequence, but we need to figure out which vacua we are really in. Yeah, just go back to the first slide, and the Yi-Zhuang has already shown is that there could be many Debye vacua, and depends on which vacua we are in, we may be able to make more precise prediction. Yeah, but anyway, you have another question about circling from.
Can I ask one more question?
Sure.
About so what do you know about the critical properties? Can you calculate in some controlled, I don't know, large n or something, what are the exponents or so on?
Right. Yeah, we haven't done that. Yeah, but sure, I think we can. So there's some understanding, like if we don't include this Wess-Zumino-Witten term, then basically all these phase transitions are just Wilson-Fisher, just you condense Higgs field. That's it. So of course we can try to do some large n or epsilon expansion to understand the exponents, and then in the presence of a Wess-Zumino-Witten term, and especially in the case that when we already considered, so basically, I think the matter fermion doesn't matter too much in this problem. Basically, all the phases are driven by different states of Higgs condensation. Even if we forget about the matter fermion, just focus on the Higgs part, I think there's already interesting things to do. For example, if this is a fractionalized phase, then this transition will deviate from the standard Wess-Zumino-Witten, and then maybe we can also consider that how to do that. Maybe start from this. We can start from a parton theory and try to do the calculation. Then in the parton theory, when we try to condense these fields, then it corresponds to a Grassmann-Wu transition, so which usually has a different exponent from the Wilson-Fisher. So yeah, sure, that there can be different things happening.
I'm a little bit confused about the anomaly matching. So usually the SU2 anomaly, it will have the odd number of fermions, but here it seems to have 16 Weyl fermions.
No. All this anomaly has nothing to do with the 16 Weyl. So note that this Cassie is not the lepton and quark Weyl fermion. That's the 10 Dirac fermions that we introduced as the fermionic partons, which already has nothing to do with the. So the new SU2 anomaly requires that you have odd numbers of spin 3/2 representation of SU2. So this is exactly the case here. We can have 1 copies of this representation 4 of SU2. This is 1. 1 is odd. So this is the odd fermions here. But you need to embed everything into here and then try to match the anomaly on a very large group, higher level. But that's the argument for why we think that there is the same anomaly for this SO10 sector by using some knowledge that we know for this SU2 new SU2 anomaly.
I see, yeah.
Because we do not, at that time, we do not have the machinery to directly maybe compute this directly from this fermion theory. So I think that's also another thing, unsolved problem to be explored in the future. Yeah.
Let me make a comment if I can. That's one's question. I think just to clarify, I think if you are worried about there is no the Witten SU2, the old anomaly in 1982 or something, that one is indeed there is no such anomaly in the spin 10 of spin 10 Grand Unified theory, where fermion is in the 16. Also not in this Cassie fermion, which is 10 dimension of the spin 10.
Right.
That old anomaly was not there, but this one is not there. But this anomaly here is the new SU2 anomaly, not the same one. These are the these are the different ones.
Yeah. I mean this new SU2 anomaly. But maybe another question is that in the field theory, we do not have the like the Z2 valued gauge field. I don't know whether is there some mathematical rigorous way to write down the Z2 value differential form.
Yeah, I don't know the answer to that. Maybe Juven, do you have comment on?
Yeah, we don't write the cohomology class.
Yeah.
Yeah, so we write, you see, B and C. But actually, we didn't write BDC, but we use this car product. This car product B car product of delta C. So these are cohomology class. So these are Z2 cohomology class. Yeah, but what's the concern about the differential form? I mean, people still can write a Z2 value the gauge field in terms of a U1 gauge field differential form and with certain level quantization to impose the constraint, right, on the holonomies of the B field on the non-trivial cycle, the manifold, such that it impose to be certain value like 0 or pi. So I mean, in certain way of writing, I think we also can write differential form. Maybe not so rigorous, but I think computationally it gives the same result. But here, Yi-Zhuang indeed showed the multiple cohomology class writing, such B and C are Z2 value the second cohomology class. So is this part clear, or any more question?
Yeah. So does this mean that the linking number in 5D can be reduced to the W to W3? I think the linking number in 5D should be at least Z value differential form.
But you can see this is this kind of term only attach a minus sign to each link, right? So if you have two link or link twice, let's say, it will be a no sign. So it will be trivial again. So it's not quite a linking number. It's more like linking number mod 2. So it's not saying that the linking number can be reduced to a Z. It's a Z2 class. It's a this sign attachment is a -1. So I think the most important thing is to check if we create, for example, we start from a fermionic partons theory. So one can try to calculate the fermionic partons theory was originally formulated in the 4-dimensional space-time. If you extend it to 5-dimensional bulk, and introduce certain kind of a link structure, and we can try to see whether there's a minus sign. If this is a minus sign, not, for example, not arbitrary U1 phase, then it has already pretty much say that it's a Z2 class, right? Otherwise, you may have an arbitrary U1 phase for the two link. So I think it's most important to check that the linking is a -1. That hasn't been fully carried out yet. I think that's also good for future research. Okay, any further questions?
Actually, I wonder whether Yi-Zhuang, you clarify the quantum critical region in the phase diagram to the audience that they do understand or not, because maybe it's not so obvious to them what exactly is the quantum critical region.
Yeah, so I want to say that. So first of all, originally, yeah, let's say, originally our motivation is try to see whether there's a quantum critical, deconfined quantum critical point between these two between these two phases. Then that's supposed to be this axis, this axis that separate on the corner of these two phases. But when we write down the parton theory and then we look at it a bit more, we realize that this parton theory actually this U1 gauge field doesn't automatically confine. So even if we break the symmetry into one of these phases, it may not immediately the U1 will confine. So it is possible that this axis may not be just a critical point, but this deconfined phase may even extend to this I mean the U1 deconfined phase may extend to these two to the symmetry breaking phases such that the U1 photon can still survive. I want to say the fermionic parton, let's say, so the fermionic parton only exists along this line, which is critical, and then the fermionic parton also may exist in the full SO10 gut theory. So this is also quantum critical. And then
exists in the sense of being gapless and
yeah, being gapless exists in the sense of exists in the low energy spectrum.
Yeah. But even for the symmetry breaking phase, they can be seen in the high energy and
yeah, they are gaps. So they are no longer in the low energy spectrum. But the photons, the U1 photons, still does not confine automatically. So that's why later we decided not to call it a quantum critical point, but a quantum critical region, because it's unsure what's the range that this critical theory will control. That there may be a range that U1 photon doesn't confine yet. So there could be a range around this axis that the theory still has deconfined U1 photons leaking out from this deconfined theory. Yeah.
Thank you, Yi-Zhuang, for a nice talk. Thank you.
Yeah, so if there's no further questions, then maybe that's it for today. And thanks everyone for coming. So please also remember to sign up the talk actively, such that we can continue to have talks in the future for this series of condensed matter journal club. So thank you, everyone. See you.